Hi everyone! Let's now move on to the third and final video in chapter 17. We want to show you how to use the PWM peripheral of the ATmega microcontroller through two interesting example programs.
Let's start with a simple program that changes the brightness of an LED continuously from minimum to maximum and then back. To achieve this, we produce an approximately 31 kHz PWM signal whose duty cycle will determine the brightness of the LED.
The hardware that is required to operate the program is very simple to build. You only need to connect an LED in series with a 330 ohm resistor. And now connect the resistor to pin 21, also known as PD7 or OC2 of the ATmega 16A microcontroller.
Here, the name PD7OC2 refers to the fact that this pin has two functions. Basically, it is the D port's 7th pin, but the OC signal of the second timer can also be accessed here. OC is the abbreviation of output compare, meaning that the result of the comparison between timer 2's TCNT and OCR registers appears to be on this pin. To make our program work correctly, we have to do the following main steps. First, we need to set the I/O ports properly so that the produced PWM signal can appear on the microcontroller's PD7 pin. In addition, the registers of the timer counter peripheral have to be set correctly so that the PWM can work in the desired mode. Let this be the triangular counter mode, which is the phase correct mode. Finally, the compare value, that is the PWM duty cycle, must be changed continuously. The main program consists of a single file called main.c, which contains the code to change the LED's brightness. The pwm.c and io.c contain the lines initializing the PWM peripheral and the ports. The comments in the source code explain what each part does, but we'll look at it in more detail in a moment. If you want to write your own program, it will be necessary to review the timer counter units in the microcontroller datasheet. The program starts to run in the main function, which calls first the IO init and the PWM init functions. The IO init does simple register writes, and the comments show the meanings of the registers. Here, for example, bit 7 of port D, that is the PD7 pin of the microcontroller, is configured as output. This is important, since this is where the LED is connected. The PWM init function sets the operation of the timer. The comments embedded into the code show what the lines refer to, but to understand it more deeply, it is recommended to review the datasheet. For example, the CS or clock select bits of the TCCR2 register affect the frequency of the PWM. The COM, or comparator output mode, bits are used to set the OC2 output to 0 when the counter is higher than the OCR2 register. Finally, the WGM bits are used to set the peripheral to phase correct PWM mode, which means that the counter value will change in a triangular pattern. The final parts of the main function have only one thing to do: change the value of the OCR2 register continuously. This is the register that contains the value, which is compared with the counter after each step, determining the duty cycle of the PWM signal. As long as the value of the OCR2 register is less than the PWM duty max maximum value, the value of the register will continuously increase, and after reaching this value, it will continuously decrease until the lower threshold is reached. But enough with the words. Let's see if the software actually works the way we want it to work. Donny, please program our microcontroller.
I'm now programming. And the program is running.
I hope you can see clearly through the cameras that the LED's brightness increases for a while, and then we're just about to see it decrease and then increase again. It's a periodic process, so we've achieved exactly what we wanted.
You can download the demonstrated source code from the curriculum's website. If you'd like to play with the code or try your own program, then you only need to write the number between 0 and 255 into the OCR2 8-bit register. In the case of 0, the duty cycle will be 0, so the LED won't light up, while in case 255 you'll get full brightness.
Another example software is also available on the website of the curriculum, which can play melodies, of course not through the LED. Let's take a closer look at how it works.
Building the hardware isn't too complicated here either. A speaker has to be connected to the microcontroller to a 120 ohm resistor. But now we will use pin 19 on the chip, which is PD5 or OC1A. The reason for this is that we are using the first timer peripheral for this task, which is a 16-bit timer, so we can adjust the output's timing in much smaller steps.
The structure of this program is a little bit more complicated. This is partly because its operation is more complicated, and partly because the program is separated into multiple source files for easier maintainability. Storing sections that belong together in separate files is a general practice in software development. This keeps files short and easy to understand. The code is contained by the files main.c, io.c, pwm.c, and music.c, and their associated headers files. In this example, the timer peripheral works in clear timer on compare match mode, or CTC for short. This mode is shown in the figure. When the values of the counter and the comparator register are the same, then not only the output changes state, but also the counter is reset and the counting starts over. The signal produced during CTC operation mode always has a duty cycle of 50%, but its frequency changes according to the value of the OCR register. This makes this mode suitable for producing a variable frequency signal. The buzzer program plays two simple melodies through the speaker. To play a melody, you only have to change the frequency of the signal. The duty cycle can stay constant. The program works very simply. The OCR values representing sounds are taken from a table in memory, so they are pre-programmed. Since this counter is 16-bit, numbers between 0 and 65,535 can be written to the OCR register, so the frequency of the generated PWM signal can be set with much better resolution than with an 8-bit counter.
It's important to explain how to read and write 16-bit registers with an 8-bit processor. The internal representation and operations on 16-bit numbers are done by the compiler, but the registers of the processor are physically 8-bit, and you can't write a higher number than 255 into them.
That's right. This problem is solved by the processor's configuration, where the 16-bit register is accessed as two 8-bit registers. The lower 8-bit in one, the upper 8-bit in the other. The problem is that we can only read or write one register at a time. When reading data from the register, this is a problem because in the time between two register accesses, something in the periphery may change, which changes the value to be read and gives a false result. This can happen, for example, when reading the TCNT register of a counter. A similar problem occurs when writing, but then the peripheral reads incorrect data from the registers while we are writing to the two 8-bit registers. This can happen, for example, when writing the OCR compare register. To solve this problem, there is a separate 8-bit register hidden in the processor. When you read or write the lower part of a 16-bit register, then the upper 8-bit is written into or read from this hidden register. This is why the order in which registers are accessed is very important, both when writing and reading. Let's take a look at the relevant part of our tune playing program. We want to write a 16-bit register to OCR1A, which we can do via the 8-bit registers OCR1AL and OCR1AH. L which ends in low, contains the lower 8 bits, and age, which ends in high, contains the upper 8 bits. The upper byte is written first, then this value is only written to the hidden register. The next write is to the lower byte, and then the entire 16-bit value is written to the OCR1A register with the hidden register in a single operation. Reading is the other way around. If we want to read the OCR1A register, we should always read the lower byte first. This way, simultaneously to our reading operation, the CPU copies the current value of the higher byte to the hidden register. When we next read the higher byte, the CPU will give us the correct value from the hidden register, which is coherent with the lower byte.
Now let's see, or actually in this situation, let's listen to find out if we can run our program.
Well, I hope we can run it. And I hope we can hear it. At least I can.
Yes, me too. This is a beautiful melody.
I hope you all recognize it. I won't tell you what it is.
I suppose hearing this wonderful symphony.
Sorry, but I'm gonna turn this off now because the people watching the video won't hear any of this. Please, you can continue now.
So, after listening to this wonderful symphony, I'm sure many of you are considering that this is not the way you want your favorite playlist to sound, but believe me, in my own experience, with a sufficiently loud speaker and a dissonant melody, you can make a perfect alarm clock.
You bet. The inner workings of the melody playing program is explained in the comments by the code, so the source code will not be further explained here. However, I suggest after understanding the operation of the PWM peripheral, you make changes to the example code according to your own ideas and create your own program.
As we've come to the end of this chapter, we hope that you have found the 3 videos of PWM useful and that you will use these signals successfully in your own projects. You will find the written curriculum and all the necessary information and links below the video. Follow us on Facebook for the latest news, and we'll see you soon in the next videos. Bye bye.
Bye!